Okay, question 8. A technician investigates different electrical devices that are used in a car. So there's the device, and that's going to be moved across when we need to. The technician connects a device to the 12-volt battery, so that's here. They want to measure the current and the potential difference. So we're going to need an ammeter that goes in series. We're going to need a voltmeter that goes in parallel. Draw on the diagram to show how the circuit should be completed so that the current and the voltage can be measured. So if I was to just connect that up now, I can now see, well, I need to put an ammeter in series and a voltmeter around the device. The next one, the technician tests a headlamp. The current is 4.8 amps, no unit change, and is connected to a 12-volt battery. Calculate the power. So we've got I, we've got V. We're going to need our IP violently formula, and we want P equals current times voltage. And again, these equations at the back for you anyway. So P equals I times V, multiply it together, 57.6. Nice, easy question. The technician tests an interior light this time. The current is 600 milliamps, so divide by 1000, 0.6 amps. 12-volt battery, and 7 minutes, so times by 60 equals 420 seconds. Now we've done those unit changes, we're ready to go, and it wants the total electrical energy transferred. So if we look at what we've got current I, we've got voltage V, and we've got T. So the electrical energy equals current times voltage times time. This is the expanded PET, because if we think P, E, T, we know power equals IV. So you can now see, yep, electrical energy equals current times voltage times time. So 0.6 times 12 times 420 equals 3024. So it's just checking you can do all your unit changes. Okay, the technician now connects 4 devices, and we can see those connected with fuses in between. The current in each device is shown. So 4.8, happy with that? Not happy with that. That's 0.6 divided by 1000. Happy with that, happy with that. It says calculate the current in the wires to the battery. So we've just got to add all of that up, making sure we change the milliamps. And that comes to 17.7. State how the overall resistance of the circuit changes when one of the devices is switched off. Well, if I remove a branch, I've got less branches, so the resistance will increase. And we've done this idea with parallel circuits. Adding branches, happy days, resistance goes down. Removing branches increases the resistance. So the resistance will increase as there are less pathways for the electrons to travel. And it also says there's a current of 2.3 in the radio. So let's delete this. There we go, there's the radio. Which of these should the technician choose to protect the radio circuit? So our choices are 1, 2, 3, 1, 3, 5 and 13 amps, and we should always pick the one that's closest and above. So 2 won't work, that will melt every time. 5 will work and is the best, it's the closest, given a choice of 10 and 13, and it's above the operating current. So B. Explain why the wires in the car battery are thicker than the wires for each of the devices. So why is it that these wires are thicker than these wires? And that's because this has got to deal with more current. And the more current it is, the more heating of the wires, and it could melt it. So we want a nice thick wire, and that'll have less resistance and prevent heating. So thicker wires will have less resistance. This will prevent the wires from heating. So more electrical current will pass to the component. It's a more energy efficient transfer.